Okay, let's get started. It's 1 p.m. So today we have two things to accomplish. The second half of the previous topic followed by today's new topic, which is k-nearest neighbors. Okay. Last time we talked about training and testing and this issue of overfitting, and the real punchline of last time was you can train a classifier or a model, see how well you did on that same data set, and be really proud of yourself that you did really well, but it's not that meaningful of a measure of how satisfied you should be with your classifier or your model, because it might be doing this thing called overfitting. And for example, with the decision tree, we can pretty much always get zero training error. And it doesn't necessarily mean we have the best possible or the perfect classifier. So we also introduced a bunch of notation. We have training examples, testing examples. We have the splitting of the training into training and validation. We have the tilde, the squiggly thing to indicate test examples, and the hat to indicate our predictions about something. Okay. And we talked about this fundamental trade-off last time, that you can play around with things, and typically you're trading off between, I can get really low training error, but that approximation term, in other words, the difference between training and testing, may become big, or vice versa. So this is this fundamental tension in the course, and getting kind of an intuition for that will be an important skill to have by the end of the course. Last time we also talked about what we're calling the golden rule, which is that the test data should not influence the training data. And I alluded to the fact that there might be kind of sneaky ways of doing this without realizing it, and we'll talk about that now in a couple of minutes. And we also, as I just mentioned, talked about this issue of splitting the data set into training and the validation. The validation set's purpose is to approximate or estimate what the test error would be. Okay, so when we just when we ran out of time last class, we were talking about this, parameters versus hyperparameters. So when we specify a model or a classifier, it's usually some type of thing. Like a decision tree is a type of thing, but there are many possible decision trees. And the thingies that determine which decision tree you have, those are the parameters. So they're often numbers. For most of the course, it'll just be a bunch of numbers. But here, they're not just numbers because, for example, you're picking which feature do I want to split on, and then you're picking the threshold, and then you're saying what you're going to predict. So you're storing all of those things, and that gives you a specific decision tree. There's something else that is going to show up a lot in this course called hyperparameters, which are more of a high-level decision controlling the complexity of the model. And by the end of today, we'll see a new classifier and a new hyperparameter, so you'll have more examples. But the main point is, if a hyperparameter allows us to make the model more complex, we can't just train it in the same way on our training set, because, for example, with the depth of a decision tree, we would always say deeper is always better, and it would be kind of meaningless. So we need some other way of picking the hyperparameters that allows us to tune a value that controls the complexity of the model. And so the validation data can help us with that. Okay. So for example, we could try a depth 1 decision tree, train it on the training set, evaluate it on the validation set, et cetera, et cetera. And we did this in the demo last class, and we produced this plot versus different depths. And then we could pick the depth with the lowest validation error. Once we do that, once we've made these hyperparameter decisions, like I want a depth 5 decision tree, before I deploy my decision tree or whatever it is, probably not a decision tree, but before I deploy my approach on AWS where customers are going to be interacting with it, etc. Well, there's probably a lot of things you want to do before that happens, but one thing you might as well do is retrain on the whole data set because you just have more data available to you. You're not going to do any more evaluating. You already decided it's going to be depth, whatever, so you just retrain on the whole data set, and it should be slightly better than the one that was only trained on the part of the data set. Yeah, your name?
Ali.
Ali, right.
Why do you need to retrain it?
Why do you need to retrain it? You don't need to. It's just that before you were only training on the part that we called the training data and you were withholding the validation data. But the point of the withholding was to do things like pick the best depth, to assess, evaluate. But once you're done evaluating, you're just going to deploy the thing. You might as well use all the data. Just because why not, basically. More data is better. Okay. Okay, so now I'm going to get into this next thing, but maybe any other questions about the review of last class? Okay, so here's a particular danger called optimization bias that you should be aware of, which is we said to not let our testing influence our training, and yet if we want to try 20 different depths of decision tree, we're actually using that validation set 20 times. And so we're kind of, there is a loop there, actually. There's a feedback loop from the validation data back to the training of the model. And in a way, we kind of contaminated our validation procedure because the whole point of validation data is it's unseen. I've never seen it before. And it's true that it is for that particular depth, it's unseen because you train on half and just evaluate it on the other half. But if you keep doing that, you actually are seeing it and allowing that to influence what happens. And so that's this issue of optimization bias. And a way that could happen is if you were trying out a whole bunch of different hyperparameter configurations, for example, maybe there's randomness in your algorithm, or even if there isn't, for some particular case, you might just get a really good score and then decide that's the best case. But it might just be luck or not a real effect. And that's more likely to happen the more you use your validation set over and over again. So that's what this effect is. So questions for you guys. There's a few of these scenarios. I built a model based on the data you gave me. It classified your data with 98% accuracy. Therefore, it should get 98% accuracy. So yes or no? Should you trust them? No. Right. So that's exactly this issue of training versus testing or validation. Good for you. You got 98% on the training set, but maybe you just used a ridiculous method like one that just stored all the correct answers, and then when it predicted, it just looked it up, and there's no learning there at all. Okay, so again, all of these things, they're not completely strict in the sense that, well, this is probably bad, but maybe if you knew they were trying some very simple models, like when I say simple, storing all the data is kind of very complex in the sense that you don't reduce the data in any way, you just grab everything. But if they're doing something very simple like a decision stump, maybe it's fine, but doesn't sound too good. I'd really like to know something about the validation error. Okay, how about this situation? I built a model on half the data. I ran it on the other half, got 98% accuracy, so therefore it should be good.
Maybe.
Maybe. Anyone else?
Probably.
Probably. Oh, yeah, right, probably. So, yeah, that sounds kind of like what I've been telling you yesterday, or Monday, and Wednesday, and today is the right thing to do, is do this split, and it's probably a good idea. Fine. Okay, so how about this? I built 10 models based on half the data. One of them did really well on the other half, so therefore that one is good. So this is where it becomes a little bit of a gray area. I'm just going from 1 time to 10 times, and I can't say there's like a limit to how many times you can do this before it gets worrisome, but this doesn't sound too terrible to me that you've tried, say, 10 different depths of a decision tree. Since there's only one hyperparameter, there's only so many values that you would even bother trying. Where it gets really messy is if you have 20 hyperparameters, and now there's so many combinations of them that you might want to try out, and then you end up trying a huge number of things. Right, so which brings us to, you do this a billion times. One of them did well on the validation set. Therefore, this is a really good model. Do you trust it?
No.
No. Right, so that's exactly this thing we're trying to get at today, this issue of optimization bias. And this is actually related to this issue of multiple testing from statistics, for those of you who are familiar with that. But you're doing something a billion times, and there is, whether explicit or implicit, some randomness in what's going on here, some effects that are hard to predict. And if you're really just doing it over and over and over again with so many different models, one of them might just do well on the particular validation set. So it's overfitting on the case where I train on this data and validate on the other data, which is a harder thing to overfit at than just overfitting on one data set. But you happen to find this thing that's crappy in general, but really good at this weird task of train on this and test on that. And that sounds like a needle in a haystack, but if you're doing it enough times, that might happen. And that's this overfitting on the validation set. Just a minute. There's a question there?
If you have enough data, is the solution to just like do more and more levels of abstraction?
The question is it a good idea to do more and more levels of validation, I guess is what you meant. So that's this. Is this what you meant? You take a third of it, you train a billion models. One of them does really well on the second piece, and then you also try it on the third piece, and it also does well. Is that what you had in mind?
Sort of, are you choosing out of the 1 billion based on the second data?
Yes.
Without looking at the third?
Correct.
Okay.
Choosing out of the 1 billion based on the second piece, and then just testing once on the third piece. So do you think this works? Yeah, I think this makes sense too. So when you're only trying something once on that third validation set, it becomes very hard to believe that something is bad in general, but just also happens to be good on this chunk of data that it's never seen before. And of course, the bigger your data set is, the better. If your validation set is very tiny, these things are more likely to happen because there's just not that many data points for which weird stuff needs to happen by chance. So having more data is definitely helpful for these kinds of things. Right. So there were other, I forget. Edwin? Yeah.
When you say a billion models, do you mean a billion different configuration of hyperparameters of the same?
The question is, when I say a billion models, do I mean a billion different configurations of hyperparameters? I guess it doesn't have to be, but that's really the situation where you would see this happen. I guess the best short answer is yes. Yeah. Name?
Ian.
Ian.
But what else would categorize, or what else would a model be if not just different configurations of hyperparameters?
What else would a model be if not just different configurations of hyperparameters? We will get to that later, but even now, so with decision trees, I don't know, maybe there were ties, like two classes were equally good, and you picked randomly which one to predict, and so therefore it's different every time you train it. And then maybe even if the depth was the same, the tree would be different every time, and so if you could get a billion different trees, but it wasn't really a hyperparameter, so that's pretty much what I had in mind. Yeah. Yeah, Miriam?
Assuming we have
Much louder, please.
so assuming we have a big enough number of set of data. So now, is there any specific relationship between test set and training set in terms of getting more reliable result on test set? I mean, for example, if we consider 10 billion data, and now we have considered half of them for test and half of them for train, it would provide more reliable data comparing with the situation that we consider 75% of the whole data as training and.
Yeah, so the question was about how much data do you set aside for training versus testing, and we talked about it a little bit last time. I can't give you a number that is always the best thing to do. We talked last time about why it would be a bad idea to use almost everything for, in one case versus the other. But actually, in a couple minutes today, we'll talk about cross-validation, which may help you with your question a little bit as well. Yeah, name?
Kyle.
Kyle.
So if we are to be training a billion models, would it be better to take like the mean accuracy model to get a more accurate portrayal of what you would expect?
Okay, so Kyle is asking if you're training a billion models, maybe it would be better to not take the best one, but to take a typical one, or maybe the second best, or the 75th percentile best, or something. I need to think about that one. Yeah. Okay. Okay, so we already talked about this. So optimization bias is the word we're going to use for the phenomenon we've been talking about. Okay, cross-validation. So getting back to Miriam's question to some extent. Doesn't it seem like a waste that we're splitting our data set and then we can't use all of this stuff for training and we can't use all of this stuff for validation? So cross-validation is supposed to be less wasteful in terms of data, which is sometimes the most precious and finite resource that we have. Sometimes it's not, right? Sometimes we have too much data and time is the limiting resource because even on 20 GPUs, the thing is still too slow or something like that. So here's the idea. There's in general k-fold cross-validation for some k, but let's talk about 5 as a concrete example. So let's chop our data into 5 sets instead of 2. And then each of those 5 sets will have its turn as the validation set. So we'll take the first one. It's your turn to be the validation set. We'll train on everything else, the other 4/5, and validate on that. Second part, it's your turn to be the validation set. We'll train on everything else and validate on that, and so on and so forth. And when we're done, we'll have 5 different validation scores, and then we'll average them to get a more robust measure of validation accuracy. So in terms of our picture of x and y, well, yeah, this is pretty much stuff I already said. So this is good because we're less vulnerable to the peculiarities of our little validation set, and we're in a way using our whole data set more efficiently, and it's like we had 5 validation sets, but we're also not really reusing any validation set multiple times, which is nice. One issue this does have is that you have to do the thing, training your model 5 times, which can be slow. So if it takes you 3 hours to train your model, then you might not want to do 50-fold cross-validation. You might only have the patience to train it once and measure it once on a validation set, especially if you're trying to do this hyperparameter optimization. It takes 3 hours to train it, but you want to try a whole bunch of different hyperparameter configurations. That loop is bad enough, 3 hours times however many times, and then this adds another loop around all that, so you're getting into things that are just too slow. Yeah. Connor.
Is there any advantage to like doing further or deeper subsets, like smaller subsets? So for example, if you were to train on folds 1, 2, and 3 and validate on 4 and 5, or
the question is if you were to train on folds 1, 2, and 3 and validate on 4 and 5. So that's sort of like just doing 3-fold cross-validation. So you can use fewer folds, and then you'll have a bigger validation set each time and do it fewer times. And there's kind of a continuum between, I guess, 2-fold cross-validation being the least. That's only twice as much effort as just the regular split train and validation, and then the other way around, all the way up to n-fold, which is like the most extreme case. So
I guess sort of more what my question is like, is there an advantage to doing multiple levels of folds on like the same data set, like doing a 4-fold and a 5-fold and a 6-fold?
The question was, is there an advantage to do 4-fold and 5-fold and 6-fold cross-validation and take the average? My guess is that it's probably better to just use your time for a larger K, but I can't prove it to you off the top of my head.
Okay.
Yeah. Anna.
If you train on like different sets, won't you get different models? So like,
Uh-huh.
if you
Yes, if you train on different sets, won't you get different models? Yes, correct. So now we have 5 models, and what do we do with them? So think of this as a procedure for assessing the configuration or the set of hyperparameters. So I want to compare a depth 5 decision tree to a depth 10 decision tree. I'll do this. You're right. Now I'm going to get 5 depth 5 decision trees, 5 depth 10 decision trees. But I don't actually care what those trees are. I just care which one's going to get a better score, which is the average of these 5 validation scores. And then I say, oh, depth 10 is better because I got a better score. I'm not going to use any of those 5 models anyways. I'm going to throw them away and retrain on the whole data set.
but like won't one depth be best for like one model, then another depth might be best for another model? Or
No, for each depth, the training procedure finds you the best model for that depth for that training set. That's what the fitting or training procedure does.
I guess.
Yeah, I mean, you're a little bit correct in the sense that if I say depth 5, it might not be the best tree ever of depth 5 because I'm not using all the training data. I'm only using some of it, but it's close enough. Okay, so as I mentioned, you can do different numbers of folds, takes longer, but should be more accurate. You can take it to the extreme and do n-fold cross-validation, which even has a name. Leave one out cross-validation because you're literally training on everything except one object and just validating on the one. And that's just the natural extension of n-fold cross-validation. Each fold just has one point in it. Okay. That is the end of finishing last lecture. Now we are going to switch gears entirely into the k nearest neighbor classifier. Any remaining thoughts on the 1.5 lectures of training, validation, and all that, overfitting? Ali?
Yeah, just out of curiosity, is there like an actual proof for why k+1 full validation is better than k full?
Is there a proof that k plus 1 fold cross-validation is better than k fold? Probably. You're averaging more kind of measures, so that this thing that was going wrong before is something bad was happening by chance or because of small numbers of measurements. And by doing things more times, intuitively it should get better. I don't have a proof for you, but I guess one exists.
Okay.
Mohammed?
If I split the data into train set and validation set and get an accuracy of 60%, then I'm doing the same but cross-validation, so I'm using the whole set in cross-validation and get 90%. Does this mean that cross-validation for this type of data is giving me a misleading intuition?
The question was, if I split into train and validation and get a 60% accuracy, and then I try cross-validation and get a 90% accuracy, does that mean cross-validation is misleading? No. If it was me in that situation, I would suspect it's the other case that's misleading, because I'd expect cross-validation to be more accurate as a measure of my ability to generalize than just a single time. Okay, last question. What's your name?
Cheyenne.
Cheyenne.
So is it possible to use machine learning in order to train which hyperparameters?
Is it possible to use machine learning to train which hyperparameters are best? So yes, coincidentally, that's what I did my PhD on. So definitely that is a thing. And we won't specifically talk about it in this course, but you're welcome to talk to me about it. Yeah. Okay. Switching gears to k nearest neighbors. So first the question of, is there something better than decision trees? So the no free lunch theorem basically tells us there is no best machine learning model that is going to give us the best generalization in any problem. And so in a way, this theorem actually justifies the existence of this course, in the sense that if there was just one best way of doing things, if decision trees were the best, then we could just end the term now. But what ends up happening in machine learning is that different problems tend to be handled well by different approaches or algorithms. And so not all, but much of this course is, here's a new method, here's a new method. And then we have other parts of the course, like last lecture, which are concepts that kind of range through the whole discipline. Yeah, I like this, yeah. It's like asking which is best between rock, paper, and scissors, right? So asking what the best machine learning model is a bit like that. Okay, so I guess I more or less said this. We need to try out different models. So actually, we're talking about hyperparameter search. Let's try different hyperparameters. It's actually common in practice to just try completely different approaches using exactly the same method we talked about, cross-validation or splitting, and not just within a family trying different hyperparameters, but even just trying completely different approaches. So the fact that we can now measure how well we're doing or approximate how well we're doing is super valuable in all of machine learning. Okay, so in the course, we focus on popular models that tend to do well on typical applications that you might encounter. And so despite what I said, just based on the way humans are and the types of problems we like to solve with machine learning, there are models that tend to be quite good, and so we're going to try to cover those in this course. Okay, here it is. KNN, as promised, 18 minutes to go. So here's what we're going to do with k nearest neighbors. When we want to classify some new test example xi, we're going to look back at our training set and find the k, again, k could be 5 or some number, find the 5 training examples that are nearest or closest to that point and have them vote. So in other words, if we're doing the I got sick or I didn't get sick allergy situation, you find I was going to eat this today. Let's look through my diary and find the 5 days that had most similar eating patterns to this day, and then check if I got sick on those days. And if I got sick 4 times and didn't get sick once, I'm going to predict that I'm going to get sick again because 4 is bigger than 1. Okay, right, so this is just what I said. Here's a new feature vector that you want to predict. You're going to look back in the training set, find similar cases, look up the labels. So those are your 3 nearest neighbors. You're all sick, so you predict sick. Okay, it's nice to think about k nearest neighbors visually. People always show it in 2 dimensions, meaning the number of features is 2, because that's how we can look at stuff. But just keep in mind that we're not usually dealing with 2 dimensions. We're usually dealing with more features, and the intuition isn't quite the same. So we have to be a little careful about that. So what is this diagram showing? It's showing 2 features, F1, F2. It is a binary classification problem like sick, not sick, meaning there are 2 classes labeled as circle and plus. And, whoops. And let's say we want to classify at the question mark. Well, the one on the right is particularly straightforward. All the nearest training examples are plus, so we classify plus. The one on the left is a little more on the boundary, but maybe there are still more circles near to it, so we predict circle. So for example, if k is 5, those are the 5 nearest neighbors in either case. And then that tells us our prediction. You had a question? Fred? Is it?
Yeah.
Fred.
Are you picking a random xi?
Are you picking a random xi? No. So I'm just showing you how I would make predictions. So it's not random. It's just like with the decision tree, I can train it, and then I can show up with some new x and then try to make a prediction. And like in the test case, that's the whole point of it in a sense. And so that's what these question marks are. So they're not random, but they're chosen for educational value. Yeah. Okay, Fed.
What does non-parametric mean in this case?
I reordered the slides to talk about that later, so it's coming in a few minutes. The question was, what does non-parametric mean? And I'll mention it later. Okay, so we talked about that. This pretty much captures the main essence of k nearest neighbors. So let's pause here for a minute. Is anyone confused by this picture, or let's maybe save more advanced questions later, because I will talk about more advanced things. But does anyone have questions or trouble interpreting this diagram? Anna?
It's not really like trouble interpreting the diagram, but you have to scale the features.
You have to scale the features. Okay, that's a sign that I should go to the next slide, because we'll get to that. Yeah. Okay, so the first thing we need is a measure of distance. So I said closest. What does closest mean? We need to compute distance in some way. That can be Euclidean distance is the most common distance. So I have 2 vectors. I want to know the distance between them. We subtract them. So I have the differences element-wise. I square all those things, add them up. Pythagorean theorem, roughly, is what this is. So what that means is, for all this to work, our measure of distance has to be meaningful. Two things close to each other, they must be similar, because we're going to borrow the labels of those nearby things. And so for this to work, the notion of distance that you're using has to make sense. And there are certain things that can arise, like Anna mentioned, scaling, and we'll get to that. Okay, so this point at the bottom is important. So the more data you have, the more complex your classifier can be. Because if I only have 2 points, then it's basically the ones over here are this and the ones over there are that. But as I have more and more points, I can have more complicated types of decisions, and we'll also get to that. So some issues with K and N. The so-called curse of dimensionality shows up a bunch in machine learning, and basically what it's saying is that my picture looked great in 2 dimensions, but if you have 100 or 1,000 or more features, you're now in 100 or 1,000 or more dimensions. And what does it mean for stuff to be close in 100 dimensions? Our intuition from our life in 3 dimensions doesn't always quite hold. And for example, there might just be nothing close to you. Or another way of saying it is you kind of want to fill the space. So wherever you are, there's something near that you can refer to. But it's very hard to fill a 1,000 dimensional space with stuff. You would just need too many points. So in terms of scales, the problem here is that if I have how much, did I get sick or not, and I have how much milk did I drink, and I measure that in liters, versus if I measure that in milliliters, K and N is going to give us different answers. And the way you can see that is imagine you decided to measure the amount of milk you had in nanoliters, or some ridiculous unit where all the numbers were really big. So I had, I don't know, 10 to the 12 nanoliters of milk, or some crazy big number today. Then these distances are going to be a bunch of subtractions, but the milk is going to dominate everything else, because it's just a bunch of humongous numbers, and then the rest just normal size numbers. And so the distance will end up, it will only really matter, did I have the same amount of milk as the other day or not? If I had the exact same amount, the difference will be 0. Otherwise, it'll just be a humongous distance. And so everything will get really messed up. The decision trees did not have this issue because if we just scaled everything up by 1,000,000, the threshold we picked would just scale up by 1,000,000. It was only really about the ordering of things. So we have to be very careful about that with k-nearest neighbors. And it's a type of thing that could go wrong if, I don't know anything about machine learning. I just install scikit-learn and then run some classifier. This could get you. Ali.
Yeah, so I'm worried about, or confused about the top part about the curse of dimensionality, because if we're caring about distance between points, why do we care about the volume of the sphere or the hypervolume?
So Ali is wondering why we care about the volume of the sphere if we're looking at distances. It's more of an intuition that there's more space to fill. So you could have a test point in some completely new part of the space that there's nothing near it because the space is just so big. It has so much volume. And so you'll get an answer. You'll find the 5 closest things. But who knows? Maybe none of them are meaningful because they're all so different from your test case. So yes, you'll always get some answer, but you could worry about whether it's a good answer. Okay, there's a lot of questions, but I have a lot to get through, so let's do a few more slides first. See where we are. Another thing you might have noticed is that we didn't have the training phase. With decision trees, we talked about training for 90% of the class, and then we hardly mentioned testing. I mean, testing is just you follow the rules of the tree, boom, done, you make a prediction. Here, it's kind of the opposite scenario. There is no training. In fact, the training is just store the data set, and then you're done. But it's the prediction that's very complicated, because then you go back, look at those points that you stored, and try to find which ones are closest. And you will be implementing this on assignment 1. So the expense, before we were worrying about n squared, n log n, d, et cetera, that was all about the time it takes to train. Now we're actually worried about the time it takes to make predictions, because we have to, for my new point, look at all n examples, and for each one, compute a distance, which is a subtraction over all d length of the vector. Okay, so some cryptic comments about making it faster and other distances, but let's move on for the moment. So to get your question fed about parametric versus non-parametric, K and N in decision trees are obviously different, but they also exemplify two general categories of models, which are parametric and non-parametric. So it bothers me a bit to talk about this right now in the sense that decision trees are not a great example. Decision trees are a bit ambiguous when it comes to this distinction, but let me just say it the way I think is helpful. So with the parametric model, you have some fixed number of things, the parameters that you want to learn. And the training phase is, can I distill all the wisdom of my giant data set by filling in those blanks? And usually they're just numbers. In decision trees, they're thresholds and feature splits and what do you predict. And then I've distilled my wisdom into these parameters, and then I'm done with my data set. And I'm just going to take that thing, the parameters, and that's all I need to make predictions. So when a new test case comes in, I'm just going to do some testing using those parameters. In the case of the decision tree, I'm following the rules, but I'm not referring back to the training data ever again. I can just throw away the training data after my training, for example, with the decision tree, because I claim to have gotten everything I need out of the training data already. So that's parametric. And this O of 1, it means there's a fixed amount of stuff rather than depending on n amount of stuff. So with K and N, in contrast, there is no such fixed amount of stuff that we're distilling the essence of the data into. We're just bringing the whole data set with us wherever we go, to whatever server we're going to live on. And whenever we want to do anything, we're referring back to that whole data set. And so if there's more data, there's more stuff that we're storing, more parameters. So people might say the complexity of the model grows with the amount of data, or the number of parameters grow with the amount of data. It's basically saying, in this case, the parameters are the data set. There's no real distilling of the data set into something else. And we just take those things around with us. Then it's called non-parametric. Sorry about the naive Bayes mention on the slide. That will be our next lecture. I just changed the order a bit. OK. Yeah, I guess I said what I needed to say here. 5 minutes left. OK. Let's do this first, and then I'll take questions on K and N. So there's more on this, a lot more on this in the bonus slides. You can take a look. But I just want to say something about norms. A norm is this double bar thing around a vector. And it's a way of measuring the size of a vector. So the Euclidean norm, or the L2 norm as written here, is the sum of the squares of x. But there are all kinds of types of norms. And there's now two 2's, so that can be confusing. So I just want to say very explicitly that the 2 on the bottom, the subscript 2, is the type of norm. And we will get to different types of norms later in the course. And the 2 on the top is just a regular 2 on the top. It's just something squared. And the reason why I'm bringing this up now in this lecture is because we were talking about distances, and I actually snuck in this notation in an earlier slide. Nobody complained. But there's a relationship between norms and distances. So a norm operates on one vector. It just tells you the size of the vector. A distance is a function between two vectors. It tells you how far apart they are. But we can represent distances as norms by saying the distance between vector x and vector y is the norm of x minus y. And I there was some confusion about this in the past with this course. So the reason why you saw a norm on that earlier slide for the Euclidean distance is the size of this vector minus that vector. That's the same thing as the distance between the two vectors. Or put another way, the norm of the vector x is like the distance from the vector x to the origin, to 0. So you can kind of go both ways with that reasoning. So this is just purely a notational thing. There's no concepts here, but we'll just be using norms a ton throughout the course. So this seemed like a reasonable time as any to say something about it. I'm just going to, I usually don't do this, but I'm not going to take questions because I just want to get through this demo in 2 minutes. So I prepared this demo for you. It's posted as usual on the course website. You can check it out. But what I really wanted to show you is that you can plot what the decision boundaries look like with these classifiers. And you will do that on assignment 1. So this is 2 dimensions, again, 2 features. Class 1 is the red dots, class 2 is the blue crosses, and a decision stump is just a threshold of one of the features. It just looks at one feature and said if you're bigger, you go this way. If you're smaller, you go that way. And so that's a visualization of what a decision stump does. The shading of blue means I'm going to predict blue in this shaded area. The shading of red means I'm going to predict red in that shaded area. I'm obviously going a bit fast here, but I want to get through it. So you can play around with this code. I think you'll find it pretty interesting. Decision trees, thinking about what they look like with all these different thresholds, one after the other, kind of nesting these thresholds. You get these interesting square-ish sort of things. So here's a full depth decision tree that gets 0 error. Now it's correctly classifying the whole training set. And I just wanted to show you K and N as well, because I think it's kind of neat. So you get these very different looking boundaries where basically the coloring of each pixel is just looking at the closest point, because that's K equals 1. And you can look at other values of K, and it'll be different every time because it's randomly generating the data set. But K in K nearest neighbors is a hyperparameter like the depth was in decision trees. And here the smaller K is getting the more complicated models, and having K being big is kind of smoothing things out, because it's saying those 2 blue points on the right, they don't do anything anymore when K is 10 because they get kind of outvoted. Whereas up there, the blue points actually did something. And so making K bigger actually makes it less complex. So I am out of time. I won't have time to go through the summary slide, but I'll just put it up and we'll end class.